Okay, in this next lesson, we're going to take a look at different models where we have reactions actually occurring, and look at different factors that affect how the models work. Now, first of all, we're going to take a look at a normal reaction. Our last unit we looked at heats of reaction and enthalpy. We can take a look at the potential energy graph here of our reactants and products, and we notice that there's a major difference between the heats of formation of your reactants and products, and this is your enthalpy. So obviously an exothermic reaction. In the next reaction, we're going to take a look at something different where our heats of formation are very close and our enthalpy change is quite small. We'll take a look and see what happens there. So we're going to take a look at this first reaction, and we're going to watch the model of what happens in a normal chemical reaction. This right here is our potential energy graph, and we notice that as the reaction takes place, we have all of our reactants forming products, and we hit 100% potential energy because all of our bonds are formed with our reactants, and the potential energy comes from those bonds being formed. So if we were to break those bonds, that potential energy could be converted into kinetic energy of any form. Say it might be heat energy, could be electricity, could be light. But we have 100% potential energy because every single one of our reactants has reacted, forming bonds. Now we'll take a look at this next reaction where we have a small difference in heats of formation and very little enthalpy, heat of reaction, and see what happens over time. And so will be interesting to note what happens. Now we can see bonds being formed, but as bonds are being formed, they end up being broken as well. Case in point, what you'll see down there. There we go. We just saw a bond breaking. And notice the potential energy never quite reaches 100%. This is the average right here where this little triangle is, and it's moving between 60 and 80%. And so we never get to that point where we have 100% reaction going to completion. We still have many reactants left over. This is what we would consider an equilibrium reaction. Now what we're going to do is take a look at some factors that might affect the equilibrium of a reaction. So again, same type of model. On this we're going to look at two factors here: equilibrium in concentration and equilibrium in temperature. So I'm just going to run this first video here, and we'll take a look at what happens. So I'm going to initially let the reaction take place. We're going to establish equilibrium, which in this case will be about 60% of potential energy, so 60% of the reaction has taken place. Then we're going to pause it, and now I'm going to go and start adding more reactants to it. And by adding more reactants, I'm changing up the concentration. So this can be done either before the reaction, say I recreate the experiment again, only I use more reactants, or we can, as the experiment is going on, the reaction is going on, dump more reactant into it, and then see what happens to the shift in equilibrium. So here I am putting a whole whack of more reactants in, so I'm more than doubling, more than tripling the amount of reactants, and we'll see what happens when I let the reaction go. Watch the potential energy graph. So we see an instant drop right away, but the equilibrium balances itself out. It's almost like it corrects itself, and we get the equilibrium that we had seen previously reestablished. So what does this tell us? It tells us that concentration does not have an effect on equilibrium as long as other factors are not changing. We're going to take a quick look at one of those other factors here, and this is temperature. So here, same type of situation. I'm going to run the experiment, let it get to equilibrium, so again around 60% completion. and because that's about as far as they'll go. And then I'm going to start bumping up the heat and seeing what happens as the heat is increased. So now I'm going to increase the heat, clicking away, and you'll see the particles start to move. Now look at what's happening to the potential energy graph. We can see that it's dropping, and we can see that the equilibrium has now shifted from making the products A2 to making the reactants the single atoms by themselves. And here we get to the point where there's no product form. So now I'm going to cool it down, and as soon as I start to cool it, we can see that products are starting to reform again, the A2 product. That doesn't mean that they always stay together. They're still falling apart at times, but we can see that the equilibrium gets reestablished again to what it was at its prior state. The last one we're going to look at, the last model here, is where we alter the dissociation energy. That's the amount of energy required to break a chemical bond. So in this case we've got reactant A2 and B2, and they are going to react to form AB. So in order for that reaction to happen, we have to break the bonds between the two A atoms and break the bonds between the two B atoms, and then they will form AB. Now depending on how strong the bonds are, that will direct the equilibrium in one direction or another. So let's take a look and see what happens here. So initially I've got the bond energy of my reactants to be quite weak compared to the bond energy of my product, and we can see from the potential energy, the percentage graphs here, that the major percentage, 0% for the reactants, and nearly 100% for the product. So now what I'm going to do is shift the dissociation energy in the opposite direction. So my reactant now, my product now has a much lower dissociation energy, and we'll see what happens. And we can see that the percentages have now shifted, so that we're close to 50% of each reactant and 0 of the product. Now I'm going to pull up the dissociation energies, make them equal for the two reactants, and make the product's dissociation energy just a little bit more. Not much more, but just a little bit more. So it's slightly favored to make more product than reactant, and we can see right away the percentages of each, where we have a higher percentage of the product being formed and lower percentages of the product, the reactants. But we can see that it's always in flux. There's the equilibrium, it's constantly shifting. Pause it one more time, and this time I'm going to make the reactants slightly more stronger in terms of their dissociation energy than the product, and let the reaction go. And we can see that the forward reaction is now weaker than the reverse, and so the reverse reaction is more favored, and we can see a greater percentage of our reactants than we can see of our products. So from this we can see that doing some tinkering we can alter which way the reaction is more favored, either the forward reaction or the reverse reaction. Throughout the course we will be starting to look at more factors that have an effect on which way the equilibrium will shift, and we'll also be able to quantify where an equilibrium stands for specific types of chemical reactions at specific temperatures.